Every time you use chat, see an AI-generated image, or hear about a new breakthrough in artificial intelligence, you're touching something much bigger than it looks. It wasn't built overnight, and it wasn't built by accident. A long time before AI became a buzzword, one quiet decision changed how all of this works, and most people never noticed it happening. That decision didn't just change Nvidia. It quietly decided who would lead the AI era and who would spend years trying to catch up. To really get the genius of this move, we have to go back to a time when Nvidia was known for one thing: making video games look incredible. The year is 1999. The world is bracing for the year 2000. That moment, everyone feared computers might break. The Matrix is blowing everyone's minds in theaters, and the PC gaming world is locked in a graphical arms race. Games like Quake 3 Arena and Unreal Tournament were pushing the limits of 3D graphics, and at the heart of it all was a new kind of hardware. On October 11th, Nvidia released a product that would define them for the next decade, the GeForce 256. They were the first to market it as the world's first GPU. Before this, graphics cards were pretty simple accelerators, though the computer's main brain still did most of the heavy work for calculating the geometry and lighting of a 3D scene. Think of a CPU like Michelin star chef. This chef can create an incredibly complex, multi-course meal all by himself, performing each step with masterful precision, one after the other. That's sequential processing. It's powerful, sure, but it's painfully slow if you suddenly need to feed an army. The GeForce 256 had a different idea. It put a transform and lighting engine right on the chip, taking the heavy math of creating 3D worlds off the CPU. Suddenly, the GPU was like a kitchen full of line cooks. Each cook handles one simple repetitive task, like chopping a single vegetable. But with hundreds or thousands working at the same time, a whole feast gets ready in seconds. This is called parallel processing. For graphics, where millions of pixels need similar calculations at once, this was a game changer. It allowed for more detailed worlds, smoother frame rates, and visual effects that were impossible before. Nvidia had essentially built the ultimate graphics engine, but here was the catch. It was only a graphics engine. The hardware was what's known as fixed function. Those thousands of tiny cores were hardwired to do just one job: draw triangles, apply textures, and push pixels onto a screen. You couldn't ask them to do anything else. And this led to a new problem. It exposed a huge untapped opportunity outside of gaming. Scientists and researchers were struggling with massive challenges in areas like molecular simulations, financial modeling, and weather forecasting. These problems shared something important with 3D graphics. They were embarrassingly parallel. They required running the same simple calculation again and again on enormous amounts of data. Our CPU master chef was painfully slow at this, handling each piece of data one at a time. What these scientists really needed was an army of line cooks. What they needed was a GPU. So they got creative. They came up with incredibly complex and tedious ways to trick GPU into doing scientific work. They would disguise their data as graphical information, colors, textures, images, then try to convert the resulting image back into useful results. It was a clever workaround, but it was extremely difficult and inefficient. There was a huge demand for parallel computing power, but it was locked inside hardware that only understood the language of video games. All that was missing was that key. Finally arrived in 2006, and it wasn't a new chip. It was a visionary piece of software. It was called CUDA. CUDA, which stands for Compute Unified Device Architecture, was a platform that did something truly revolutionary. It unlocked the GPU. For the first time, it gave developers a direct and relatively easy way to program Nvidia's GPUs for all sorts of general-purpose tasks, using familiar programming languages like C. The army of line cooks could finally be given new recipes. Announced in late 2006 and officially released in early 2007, this decision, led by Nvidia's founder and CEO Jensen Huang, was not an obvious one. In fact, it was a massive gamble. The company poured money into developing CUDA, a project with no guaranteed market and zero immediate revenue. To Wall Street, it must have looked like a bizarre distraction from their wildly successful gaming business. Why spend a fortune building a tool for a handful of scientists when you could just be selling more gaming cards? But Huang saw something everyone else missed. He understood that GPUs weren't just for graphics. They were fundamentally parallel processors. He believed the future of computing wasn't just about making CPUs faster, but about accelerating specific, demanding jobs with specialized hardware. To him, the scientists struggling and hacking their graphics cards weren't a small niche. They were a flashing warning sign pointing to where the entire industry was going. So what did Nvidia do? They didn't just release CUDA and hope it would catch on. Instead, They quietly began a long, patient mission, one that would take more than a decade, build something much bigger. They released software development kits. They built libraries of ready-made code for common tasks, like CUDNN for deep neural networks. They ran workshops, funded university research, worked closely with developers to help them move their applications onto CUDA. They made it as easy as possible to use Nvidia hardware for things that had nothing to do with gaming. It took 13 years for Nvidia's developer program to reach 1 million registered users, but it took less than 2 more years to reach 2 million. By June 2024, Jensen Huang announced that there were 5 million CUDA developers worldwide. What Nvidia was building wasn't just a product, it was an ecosystem, a fortress. Developers who spent years learning CUDA and optimizing their software for Nvidia GPUs weren't going to walk away easily, even if a competitor released a slightly faster chip. Their code, their experience, and their entire workflow were now deeply tied to Nvidia's platform. This created a powerful, competitive moat, one that rivals like AMD and Intel, still largely focused on CPUs or fragmented software strategies, would struggle to cross. Let's rewind to 2012, to the visual recognition challenge that changed everything. A team from the University of Toronto submitted a model called AlexNet. It didn't just win, it dominated the competition. Previous winners had error rates of around 25%. AlexNet achieved 15.3%. This sudden leap forward shocked the computer science world and ignited the deep learning revolution. How did they do it? The key behind AlexNet wasn't only a clever neural network, it was the hardware used to train it. The model was so large that training it on a CPU would have taken months, if not years. Instead, the researchers used 2 Nvidia GeForce 580s consumer gaming cards and programmed them using CUDA. This was the moment of validation. Everything Nvidia had bet on back in 2006 led to this point. At its core, deep learning is made up of massive matrix calculations, the exact type of parallel work GPUs are designed for. AlexNet proved that for the new era of AI, GPUs weren't just an option, they were the only real choice. The company had already expanded into data centers with professional GPUs. Now, it began designing hardware and software specifically for AI. It introduced chips like the V100, A100, and H100, each featuring specialized tensor cores built to speed up AI workloads. It also launched DGX systems, complete AI supercomputers in a box that labs and companies could deploy instantly. Today, Nvidia's dominance is almost absolute. By some estimates, the company controls more than 70% of the AI accelerator market. Its GPUs power nearly every major AI model, from large language models like ChatGPT to image generators that create art from text prompts. Nvidia became the first semiconductor company to reach $1 trillion valuation, and by early 2026, its market value had climbed past $4.5 trillion.